Hi, in this video we are going to implement Bellman Ford algorithm together, so let's get started. I'm going to create 4 classes. One class for the edges, as we have seen for Dijkstra algorithm, one for the vertices. Basically, these 2 classes are going to be very similar to that of Dijkstra's algorithm. Okay, I'm going to have the Bellman Ford and the app.java from which we are going to test our application. Okay, so as far as the edge is concerned, I'm going to have a private double weight. Basically, these are the edge weights as usual. We will have a vertex, start vertex, and we will have a private vertex, target vertex. I'm going to right click and source generate constructors using fields. Okay, I'm going to get rid of the super. I'm going to right click and source generate getters and setters for the start vertex, for the target vertex, and for the weight as well. Ctrl Shift F to auto format, and basically that's all about the edge class we have been talking about in the Dijkstra's algorithm implementation. The vertex class is going to be very similar as we have seen in Dijkstra's algorithm. So first I'm going to have a private string name. I'm going to have a private boolean visited to track whether we have visited a given vertex or not. I'm going to have a private double distance. It's going to be the distance from the start vertex, maximum value. I'm going to have a reference to a vertex, basically the predecessor or the previous vertex in the shortest path tree. And basically we have the adjacencies, so a list of edges. I'm just going to call it adjacencies. Okay, I'm going to import the java.util.list, and of course I'm going to correct it because it is edge instead of edges. Okay, I'm going to have a constructor for the vertex. Okay, basically it's going to have a string name, and this is how we initialize the name variable. I'm going to instantiate the adjacencies list. It's going to be an array list. And I'm going to have a public void add neighbor. It's going to have an edge, and this.adjacencies.add, and we have to specify the edge. So basically we add a new edge to the adjacencies list. I'm going to override the toString method, and I'm going to return this.name. And I'm going to generate getters and setters for all the field variables. So adjacencies list, maybe I'm not going to use them, but whatever. Ctrl Shift F to auto format, and let's save it. Okay, then the Bellman Ford algorithm is going to be a bit trickier. We are going to have 3 methods. First of all, I'm going to have a reference to the list of edges. So it's going to be the edge list. I'm going to have the list of vertices, the vertex list, and basically that's all. In the constructor, we are going to have a list of edges, basically these, so the list of edges, and then the list of vertices. So we are going to inject it via the constructor. So this.edgeList is equal to the edge list, and this.vertex list is equal to the vertex list. Of course, we have to import the java.util.list. Okay, then we will have the public void Bellman Ford algorithm, for example. It's going to have a vertex, for example, start vertex, or source vertex, whatever. Okay, first we have to initialize the source vertex So source vertex dot set distance to be 0. We have to initialize it like this because this is where we are standing. So the distance from the given node where we are standing, of course, is 0. Then we are going to have v minus 1 iterations, as we have discussed in the theoretical section, where the v denotes the number of vertices. So the integer I is equal to 0, and while the I is less than the vertex list dot size minus 1, we are going to make v minus 1 iterations. And basically on every iteration we are going to relax all the edges. So that's why we have to iterate through the edge list as well. So we iterate through the edge list as well. And basically if the edge dot get start vertex dot get min distance, get distance is equal to the double dot maximum value, we have to continue. I'm going to talk a bit more about it. Anyways, I'm going to define a new distance. So the new distance is equal to the edge dot get start vertex. Basically, it is the same as we have discussed for Dijkstra's algorithm implementation. We get the distance plus the edge dot get weight. What does it mean? We would like to make sure that the vertex we are standing has a certain distance from the source vertex, and this is how we are able to get it. Of course, we have some extra cost if we would like to visit all the neighbors, because basically we are going to iterate through v minus 1 times and going to relax all the edges at the same time. So basically we consider all the neighbors for all the vertices on every single iteration, and we make v minus 1, so the vertex list that size minus 1 iterations. And we have to calculate whether is there any better solution. What does it mean better solution? That a shorter path. And if the new distance, again as we have seen for Dijkstra, is smaller than the edge dot get target vertex dot get distance, it means that there's a better solution. So first we have to update the edge, so get the target vertex that set distance to be equal to the new distance, and we have to set the predecessors as well. So we get the target vertex dot set previous vertex edge dot get start vertex. Maybe it would be a bit better solution to get the start vertex and the end vertex. Yeah, maybe it's going to be better. So I'm going to have a vertex, for example, u is usually the start vertex, so get the start vertex. I have the v. I don't know why, but applied mathematicians usually use symbols like u, v, alpha, beta, gamma, and so on. Not so talkative in object-oriented programming, but whatsoever. So the edge dot get target vertex. And basically edge dot get start vertex is going to be the u. The edge get start vertex again is going to be the u. Then here the target vertex is going to be the v. Then we have to update the v and we have to set it the u. Maybe a bit better solution to do like this. Okay, and basically this is why we relax all the edges, so we have to iterate through all the edges v minus 1 times. So v minus 1 iterations, we relax all the edges. So this is how we do it. We do another iteration. So we iterate through again over the edge list, and if we bump into a situation when the new distance is going to be better, then we know for certain that there's a negative cycle. Okay, why? Because v minus 1 iterations make sure that we have considered all the possibilities, all the routes, so it is not possible to do any better unless we have a negative cycle. First we have to check whether the edge dot get start vertex dot get distance is not equal to the double dot maximum value, because it means, of course, that there cannot be a negative cycle. We just don't consider that value. Okay, and we have to check whether if has a cycle. I'm going to implement this method on the given edge. Of course, it's not an f function but the if function. Then I can say that, for example, I system out println that there has been a negative cycle detected. And of course, I would like to return. So, okay, you may pose the question that what is this function, this has cycle? Basically, it is the same as for here. So we get the new distance, which is basically the edge.get start vertex.get distance plus the edge.get weight. So basically, this is the vertex where we are standing and we visit its neighbor. So this is the get distance is going to return the cost so far from the source vertex, plus we have some edge weight. And if it's smaller than the edge.get target vertex dot get distance, and of course we have to return it, it's going to be a boolean. So if this is true that this plus this is smaller than the target vertex get distance, it means that the overall cost has been changed, which means that there is a better solution. And because we have already considered all the possibilities in v-1 iterations, the only way the overall cost can change if there is a negative cycle. So basically that's how we are able to detect a negative cycle, that we make v-1 iteration, and basically this is the with iteration. And if in this iteration we again come to the conclusion that the overall cost has been changed, then we know for certain that there's a negative cycle. Okay, and we will have another method, basically the public list of vertices shortest path to vertex and the target vertex. And basically here I'm going to check whether this target vertex dot get distance is equal to the double dot maximum value. It means that there is no path from the source to the target. And anyways, I'm going to have an actual vertex is equal to the target vertex. And while the actual vertex is not equal to null, or sorry, the actual vertex dot get previous vertex or get predecessor is not equal to null, we are going to backtrack basically and print out the actual vertex. So the actual vertex plus some spacing, for example, like this. And this is how we are able to track the shortest path. So the actual vertex is equal to the actual vertex that get previous vertex. And sorry, it's going to be a void. Okay, so this is how we are able to track. If the get distance is equal to double that max value, it means that we are not able to find the shortest path because there is no route to the target vertex. But anyways, that's why we update the previous vertex or the predecessor on every iteration, if possible, because this is how we are able to track the shortest path. And if you would pose the question that what vertices are on the shortest path, then okay, this is how we do it. We have this while loop, and while the get previous vertex is not 0, we are able to backtrack the vertices starting from the target vertex. Okay, so that's all about these methods. In the next video we are going to test our application. Thanks for watching.